Oh, hey girl, how's it going? Today we're going to have a look at the Level 2 Chemistry exam from 2023. That's last year. Cool. We're going to understand bonding, structure, properties, and energy changes. It's going to be very exciting. We're going to have a whole lot of fun. This one was, I reckon, one of the more easier externals, so that's great. And we're going to go through question 1, and it's going to be very exciting, and we're going to learn some things, hopefully. And, yep, I can't wait. I remember doing this, it was just a whole lot of fun, Level 2 chemistry is fun. You're having a great time, I'm sure you are. I'm having a great time too, going back and going through the questions, so let's get into it. Okay, so, question number 1. Ethanol can be used as a biofuel. Biofuels are formed from materials made by living organisms. Now that's very cool, that's quite fun, okay. So the production of ethanol and carbon dioxide from glucose is shown here in this equation. Perfect. I got a little extra diagram here if you want to see. Look at that. Glucose, yeast, goes to ethanol, carbon dioxide. So you can see here it's like 2 molecules, number 1 and number 2. Okay, that's fun. That's just a little fun diagram. We don't actually need that. Okay, we can move that. Okay, question 1. Where were we? Is this process an endothermic or exothermic reaction? Provide a reason with your answer as well. Cool. Very simple achieve question here. Let's go through it. So, we look at the reaction, and you can see it's given us a value for the delta H of negative 72 kilojoules per mole. Perfect. So all we need to do is look, is this a negative or a positive number? If it's negative, it's exothermic. If it's positive, it's endothermic. So we can write, this is exothermic. Amazing. I love it. Super simple. Now, so why is it exothermic? Well, if we have a little look here, what does delta RH actually mean? So delta means the change, just a symbol for change, very cool. R is the reaction, so that's great. And then H is the enthalpy. So it's the change in the enthalpy of this reaction here. Cool, and it's saying it's negative number. So that must mean that the products, because if we have this equation, delta RH is equal to the enthalpy of your products minus enthalpy of reactants. Perfect. So therefore it's showing that the products have a lower value of enthalpy than the reactants do. Okay, and now what is enthalpy? It's just heat energy. Well, in this context, constant temperature and pressure, enthalpy is heat energy. So we're saying that it has released heat energy because the products have less heat energy than the reactants. So this negative number is just saying it's releasing heat energy into the environment or into the surroundings. So that sounds like a great reason. So we can write that one down. Exothermic, it releases heat energy to surroundings. And how do we know this? Because it has a negative delta RH value of negative 72. Do we need to write that? Probably not. But yes, negative delta RH value. Perfect. Okay, so it's just an achieve question, this one. We got exothermic and we have a reason. Beautiful. Now, if we're moving on to the second part of the question, we can probably delete this. Okay. Beautiful. So now it's saying, draw a labeled energy diagram for this reaction. We want to show reactants, products, and the change in enthalpy, which we just kind of went over. Cool. Yeast is a catalyst, so don't include it in the diagram. Okay, so we don't need to get worried about yeast. We'll have a little look at it after we've done the question though. Okay, cool. So what are we going to do first? Let's start with the reactants. You can just choose a random spot to put it. Doesn't really matter, but we know that it's releasing heat energy, so let's just start it up at the top somewhere. Oh, that's the eraser. Okay. Beautiful. Now, we can call this the reactants. They just start there. That's very cool. What are they? Looks like it's just glucose. Okay, so we can write C6 H12 O6. Beautiful. Now, where on this diagram is the products going to go? Well, I think we can tell from what we did earlier, as we have a negative change in enthalpy, and we know this because enthalpy here, products minus reactants. So if you can do some math, we know that the products here are going to have a lower enthalpy value or heat energy. Cool. So let's write what the products are. Ethanol and CO2. Okay. 2 ethanol. What is ethanol? Can we just write in it? CH3 CH2 OH, and we also have 2CO2. Do we want to put, look, we can put states as well. Is this needed? Not 100% sure, but like for NCEA, let's just make sure that we put, everything in, just in case they want to take some marks away from us. We don't need that, so just try to include everything. You can always write more, and that's fine, but if you write less, they can take marks off. So, okay. Perfect. So we have the reactants. Higher amount, oh, jeepers. Reactants, higher amount of heat energy. Products, lower amount of heat energy. Now, if we go like this, and draw a little arrow here, let's just do a little dotted line. And this is your change in enthalpy. And we know from before, it's negative 72 kilojoules per mole. Amazing. We've got the change of enthalpy, we've got the products, we've got the reactants. Show reactants, products, the change in enthalpy. I'm pretty happy with this. I like it. We've got all the things they want, and this is just emphasizing the point we made up here of how it releases heat energy. Reactants, higher heat energy, they're up here. Products, a lower amount of heat energy, and we know energy can't be like destroyed or created, usually, hopefully. So that heat energy's got to go somewhere, and where's it going to go? It's going to go out into the surroundings. Perfect. Should we have a little look at actually what is going on in the real world? I got a diagram here if you want to see. This is not related to NCEA, but let's just see. So it's actually like multiple steps, not just one. That's cool. You can go from glucose. The yeast has got ADP, ATP, goes through this thing, multiple steps, goes to ethanol. Cool, that's exciting. So there we go. Chemistry is more advanced than level 2 chemistry. Who would have guessed? Yeah. Okay, very fun, very exciting. I think we're doing great so far. I hope we're having a great time. I am. Okay, we're moving on. Question III. How exciting. Let's see. Calculate the energy change when 161 grams of ethanol is formed. Cool. We are given the molar mass of ethanol to be 46.0 grams per mole. Okay, so we're going to do a little calculation here, do some math, exhilarating. So what are we wanting to do? Calculate the energy change. If we think about the question, it's wanting an energy change. What is energy? You usually measure that in like joules or kilojoules, right? That'll be energy. Do we have any more information earlier on? Yes, in fact we do. Look at this thing right here. Oh my gosh, that's so exciting. We have something that looks like an energy. That's in kilojoules per mole, but energy, perfect. So we could probably use this as well. Now let's get back to it. Let's see what we're going to do first. 161 grams of ethanol. Seems a bit weird to measure ethanol in grams. Usually it would be in mils, right? But you can convert between grams in mils just with density. Not needed here, but we'll start off with, so 161 grams of ethanol. We have the molar mass. Now we know there's a fun little equation that says N is equal to your mass divided by your molar mass. Now that's great. We love that. Probably a good idea to remember that. There's a way that you don't have to remember it, which maybe I could cover in another video if you're interested, called dimensional analysis. I never have to remember equations ever again because you can just use the units. But that's beside the point. So we can start here. We can go N, the number of moles of ethanol. Let's just write ethanol. That is equal to a mass divided by a molar mass. Do we have a mass? Yes, we do. It's 161 grams. Divided by, do we have a molar mass? We sure do. This is great news. 46.0 grams per mole. Excellent. So now we can put that number into our calculator, and I've just done this earlier, so I don't have to get a calculator. It's 3.5. Yep. Should we go 3.50? That's a 0, I promise. Okay. Beautiful. So now we've worked out that 161 grams of ethanol is 3.5 moles of ethanol. Excellent. So, calculate the energy change when 3.5 moles of ethanol is formed. Okay, let's go back to the equation. Here we have glucose going to 2 mole ratio of ethanol and 2 CO2. We don't need to worry about glucose, we're not talking about that, or CO2, we're talking about ethanol. And this bad boy right here, delicious. So, this is saying that when you react and form 2 moles of ethanol, it releases 72 kilojoules of energy. Okay, let's get this down to see how much energy is released when 1 mole of ethanol, because that's a much easier number to work with. There are multiple ways to do this question. I find this to make a lot of sense. So 2 moles of ethanol, when that's formed, releases 72. Okay, so how about 1 mole? So all you have to do there is go negative 72 divided by 2 is equal to, I could do this in my head, but I've done it earlier. Yes, 36. Okay, so negative 36 kilojoules per mole. Because we've divided by 2, so that's saying when 1 mole of ethanol is formed, it releases 36 kilojoules. Incredible. But do we have 1 mole of ethanol? No, we don't. We have 3.5 moles of ethanol. So all we have to do here is go 3.5 moles times negative 36 kilojoules per mole. Okay, and what does that equal? Let's just have a little look. Calculated earlier. Okay, negative 126. Make sure that it's beautiful. Okay, so we've worked out that 126 kilojoules of energy is released when 3.5 moles of ethanol are formed. Let's go through this one more time. So, what do we start off with? A mass. Hard to work with mass. Let's turn that into moles first. We did that, and we got 3.5 moles of ethanol right here. That's really good. Maybe you'll get an achieve mark for that. But this is a merit question. Let's go even further. We saw that this equation showed us that when you form 2 moles of ethanol, it releases 72 kilojoules. We don't want that, so let's turn it into 1 mole. 1 mole of ethanol equals negative 36. Okay. Do we have 1? No, but it's easy to go 1 times 3.5 moles to get 3.5 moles of ethanol. Perfect. So you have to times 3.5 moles. There we go. By negative 36, and you can get negative 126 kilojoules. So the negative sign here just means that it's released. So you can say the energy change is either negative 126 kilojoules, or you can say 126 kilojoules energy released. Amazing. Great work. We did it. And that is also in 3 significant figures, which all of chemistry is at level 2 chemistry, at least. So very good. Fantastic. Great work. I'm so proud of everyone. We're going great. Should we move on? Okay, let's move on. Okay, cool. Question number B. The Lewis diagram for ethanol was shown below. Lewis. Okay. We got some bond angles. Perfect. What's the question? Compare and contrast. The NCEA loves a compare and contrast. The shape and bond angles around the carbon and oxygen atoms in ethanol with reference to Vesper theory. VSUPR. It's like a little Vesper. Meow. Here's someone sitting on a... Okay, what are we doing? Chemistry. That's what we're doing. We're not drawing Vespers. Okay. Now, this question is a super easy excellence question to get. All you have to do, the best way to do it is to remember a writing frame. And we're going to go through that. Hopefully you've been taught this. So we'll go through the writing frame, and then maybe I can sort of explain a little bit more of the chemistry afterwards. Okay, that sounds great. Who's excited? I'm pumped. Okay. Let's go. Let's start with carbon. You could do both at the same time, but then it's a bit confusing. Let's start with carbon. So, we have a look here. There's definitely carbon. We want to compare and contrast things. Let's go. So, that's a T. There are 4 regions of electron density around the carbon atom. Well, there's 2 of them, isn't there? We could do one at a time, but we'll just do carbon. They both have 4 regions of electron density. So we'll say around the carbon atoms in ethanol. Incredible. First sentence. It's going to be the same for anything you do. Next one. These regions repel for maximum separation to minimize. This is I'm terrible at spelling, but we're going to pretend that it's right. I don't even know. Maybe that's right. To minimize, it wants to minimize repulsion. Okay, beautiful. Next sentence done. Now we say this gives a parent geometry of tetrahedral. Yes, it does. With bond angles of 109.5 degrees. Awesome. Now, is that making sense? Yes, it is. We've got 4 regions of electron density, correct, around the carbon atoms. These regions repel for maximum separation to minimize the repulsion. This gives a parent geometry of tetrahedral. Now, why do we know it's tetrahedral? That means because there are 4 regions. Number 4, tetrahedral. Perfect. Now, how many bonding regions? 1, 2, 3, 4. It looks like they've got 4 bonding regions. Very good. Those are bonds right there. Do we have any non-bonding regions? No, we don't. So we can say that. There are 4 bonding regions and 0 non-bonding regions. That's correct. We love it. 4 bonding regions, 0 non-bonding regions. So the overall geometry is I can't spell. Tetrahedral with bond angles of 109.5 degrees. Beautiful. Perfect answer for the carbon bit. I love it. Okay, that was pretty easy because they're all bonding. There's no non-bonding, so the parent geometry, tetrahedral, that is what the overall geometry is. Let's have a look at oxygen now, and then we can compare and contrast. Okay, so oxygen. Let's start off. Well, let's just make it nice and easy so we know what. Boop, that's there. Boop, oxygen. Okay, there are. Should we count them? Count the regions? 1, 2, 3, 4. I like it. Okay. There are 4 regions of electron density around the oxygen atom in ethanol. Beautiful. Now, the exact same sentence, can I use technology? Oh, this is going to be great. Let me just copy and paste, because that's really what this question requires. It's a copy and paste sort of vibe. Duplicate. I mean, it sort of worked. Is this making it more confusing? I hope not. Okay, there are 4 regions of electron density around the oxygen atom in ethanol. These regions repel for maximum separation and to minimize repulsion. Yes, they do. Cool. Now, what do they repel into? What shape? What are we making? Again, this gives a parent, or overall, nope, not overall, parent geometry of tetrahedral with bond angles of 109.5 degrees. Very good. Okay, now this is when things get different. Things get super exciting. Let's go. How many bonding regions versus non-bonding regions? Okay, let's look at some bonds. That's a bond. Very cool. That's a bond. Should we change color? This is non-bonding. This is also non-bonding. Wow. Okay, so we got some different things going on. What do we got? 2 bonding regions and 2 non-bonding regions. Ooh, exciting. Okay, let's write that, and then, jeepers, then we can think about it. So, there are 2 bonding regions and 2 non-bonding regions. Amazing. So then we need to think about, what does that mean? Now, I hope I've got a little diagram. Did I attach that? No, because that would be way too easy. Where did it go? Okay, I'm back. It's like I never left. I had this image here the whole time. Okay, so we've got, this is just sort of telling you, it's like a little map of where you go. So we started off with 4 regions of, oh, that's a circle, of electron density. Excellent. And how many bonding regions? We have 2 bonding regions and 2 non-bonding regions. So right here we've got 2 non-bonding pairs. So that means the overall structure is going to be bent, and it still has that 109.5 degrees. Very cool. And if we use this diagram, we could do the same for the carbon. 4 regions, and we have no non-bonding, all bonding, and it's tetrahedral. Perfect. So we were right with the first one. Very good. Okay, so we don't need this diagram. This is sort of something that you just have to remember. There's not a whole lot to remember. It's mainly like there's going to be 4, 3, or 2 regions. And then for 4 regions, you could have these 3. For 3 regions, you could have these 2. And 2 regions is just linear. A little bit of remembering, but that's sort of how NCEA rolls. You know, they love making you remember things. But it's the best way. So just remember these. It's not that much to remember. It gets worse in level 3. So just be happy that you've only got these. Okay, let's continue. What do we find out? So there are 2 bonding regions and 2 non-bonding regions. This gives an that's how you spell overall geometry of bent with bond angles of 109.5 degrees. Amazing. Great work. We've really went out here and did it. Okay. Let's go back to the question and see what we're going to do next. Compare and contrast. Now that is something we haven't done. About carbon and the oxygen. Okay. So let's just do a little compare and contrast sort of vibe. Use the words compare and contrast. That'll make them think that you're actually doing something, I think. Okay. So, while carbon... let's just go, while the carbon atoms, wow, I really am bad at writing. While the carbon atoms in ethanol have a tetrahedral geometry. Can you just say contrastly? That's not a word. Just, okay, I don't know. Well, the carbon atoms and ethanol have a tetrahedral geometry. Oh, here we go. In contrast, this is great. This okay. The oxygen atom is bent geometry. Very cool. And now so that's a little contrast, and then let's compare as well. Let's put the bond angles in because we worked those out. They both have bond angles of 109.5 degrees. Should we give it a reason why? Oh, they might love that. Bond angles of 109 as they both have a parent geometry of tetrahedral. Incredible. Wow, what a great, there we go. Excellence, easy excellence marks, right? That wasn't too bad. Just remember the writing frame and plug in the numbers. That's just the best way to do this sort of question. And they always have this sort of stuff, compare and contrast, or just like explain the bond angles and geometry. So super easy. I believe in you. Should we kind of go like talk a little bit about chemistry and not just memorizing stuff? Should we learn things? Sure. There are 4 regions of electron density. Yes, there are. Here they are here. These are electrons. Because what is a bond? A bond is just the sharing of electrons. In a covalent... I can speak. In a covalent bond, that's just the sharing of electrons. So here, electrons. What is the charge on an electron? It's a negative charge, right? So they're going to repel each other, because like charges repel, makes sense. So that means that they're going to get away from each other as far as possible. And if there's 4 of them, the way that they move to be furthest apart from all each other is just happens to be that the bond angles come out to 109.5. Like for example, if there's only 3, let's just go like this. Draw BH3. Here we have 3 regions of electron density around the central boron atom, and this can be a nice flat sort of vibe. So these are 120 degrees, and that's the furthest that they can spread out, so they're happy. They're not pushing up against each other. That's sort of why we have these bond angles, because electrons want to get away from each other. Oh, hey girl, I'm back. My phone ran out of storage. I love that. So it stopped recording, but we're back. We're here. It's a whole new day. We're going to finish off with question number C. Hope you're loving it so far. Hope you're learning things. I'm having a great time. So let's kick on. Let's do question C. Okay. So ethanol is the major component in alcohol-based hand sanitizers. Yes, because ethanol is an alcohol. Cool. A student noticed that after rubbing the hand sanitizer on their hands, it readily evaporated, leaving their hands feeling cool. Very cool, very cool. The equation for the evaporation of ethanol is shown here. Awesome. What do we got? Ethanol going to ethanol. Great, but we've got a liquid going to a gas. Yes, in evaporation. Okay. So, circle the word that describes the change in enthalpy, delta RH, again, very cool, for the evaporation of ethanol. So, is it a positive or a negative delta H? So this again is asking, is it endothermic or exothermic? Now, let's have a little look at the clues in the question. What do we have here? It's an evaporation, so maybe you just know that evaporations are endothermic. Or if you didn't know that, you could have a little look here and it says, leaves the hands feeling cool. Okay, so a student's hands is like the surroundings. Well, you hope your hands are not the reaction, right? So that the student's hands are the surroundings. So if it's feeling cool, or the heat energy is decreasing from the surroundings, therefore it must be endothermic and have a positive delta RH. Okay, because remember in the last one, what do we do? What do we got here? We had an exothermic one, didn't we? With a negative delta RH that was releasing heat energy. Now this is just the opposite. It's absorbing heat energy from the surroundings. So therefore, the surroundings are getting a little bit chilly. Okay, very good. Okay, so positive delta RH, we love that. Now, we probably should explain what's going on. So explain why ethanol readily evaporates and why the evaporation of ethanol results in the student's hands feeling cool. In your answer, what should we do? Consider the transfer of energy occurring during the evaporation process, and then also refer to the structure and bonding in ethanol. Okay, let's start off. I'm going to start off with doing the bottom bullet point first, just because it makes more sense. Okay, let's think about what sort of substance ethanol is. Is it metallic? It doesn't give metallic vibes. Is it an ionic substance? Probably not either. So ethanol is... I know you're on the edge of your seat, I am too. Ethanol is a molecular substance. So there's some easy ways to figure out which sort of substance is what, like what's ionic, what's metallic, and the other things. Maybe we can cover that in another video if you're excited. But there's like, I don't know, like 4 different sort of substances that you need to know. You'll find like further on there's probably a table and you need to list them. So another fun thing to remember, but let's just say that we know ethanol is a molecular substance. Yes, and therefore it has, is there an E on the end of therefore? I have no idea. Yep, you can tell that I didn't do very well in English. Therefore, it has weak intermolecular bonds. between the ethanol molecules. Yep. So a molecular substance has weak intermolecular bonds. Okay, let's have a look. What are they? Now we can do a little drawing. How fun. Let's draw ethanol. We've got a CH3, CH2, O, bonded to H. Cool. Okay, let's draw another molecule of ethanol. Where am I going to do this? Maybe over here. CH3, go backwards, CH2, O, H. Cool, so we have one molecule of ethanol here and another molecule of ethanol here. Now, what are these weak intermolecular bonds? Let's have a little look. Maybe I'll even change my color. Red for weak intermolecular bonds. So these bad boys, especially, in, what are we in first? The liquid phase, right? We're going to have these bonds that come between the ethanol molecules, such as maybe between the hydrogen here and the oxygen of another ethanol molecule. So this is a hydrogen bond, and this is a type of weak intermolecular bond. So this is holding together two different ethanol molecules. So these bonds are relatively weak, even though hydrogen bonding is quite a strong type of intermolecular bonding. But in the grand scheme of things, these intermolecular bonds here are very weak compared to the much stronger covalent bonds that are like here or like here, that are between the actual atoms in ethanol. So you're not going to break these covalent bonds, but it takes only a little amount of energy to break. I'm trying to get a cool pen. Let's just, whoa, this bond's breaking. Yes, it is. Okay, so that's breaking a weak intermolecular bond. And now, whoa, evaporation. That was sick, wasn't it? I hope you enjoyed. Okay, brilliant. So we found out that we're not going to be breaking covalent bonds, but we can break these weak intermolecular bonds quite easily. Okay. So how are we going to put this into the answer? Okay, so ethanol is molecular. Cool. It's got these weak intermolecular bonds between the ethanol molecules. Molecules. Yep. Therefore, these only require a, yep, that's an S, small amount of, let's be more specific. What sort of energy? A small amount of heat energy to break. Okay, perfect. So what does that mean? That means that ethanol can therefore readily evaporate. Yep, because doesn't require much energy at all, and then you can break these intermolecular bonds, and then ethanol can evaporate. Awesome. Okay, so what have we done so far? We've referred to the structure and bonding present in ethanol. We did that. Tick. Nice. Okay, cool. So what are we doing now? We have to consider the transfer of energy occurring during the evaporation process. Okay, so what do we know about what's going on? So we know evaporation is endothermic. We found that out before with a positive delta H. Very cool. Let's start by writing that down. The evaporation of ethanol is endothermic. Now, why is it endothermic? Well, it needs to get the energy from somewhere to break these intermolecular bonds, so it's got to absorb energy from its surroundings. Okay, so let's probably write that one down. So it's endothermic as it absorbs the heat energy from the surroundings. Okay, now what are the surroundings here? Well, it said earlier that it's on a student's hands, right? The hand sanitizer. Yes, very cool. Okay, so let's say it absorbs heat energy from the surroundings. Okay, well, how about we just like yoink and get rid of that and say instead of the surroundings, let's not be super vague. It absorbs the heat energy from the student's hands. Perfect. So that's how it's getting the energy to break these intermolecular forces, because it's absorbing the energy from the student's hands. Cool. Okay. And now we can say as heat energy is absorbed from their hands, their hands now feel cool. Yes, because it's taken away some of that heat energy from the students' hands, and now they're feeling colder than before. Okay, I'm pretty happy with that. Let's just check. Did we refer to the structure and bonding in ethanol? Yes, we said it's molecular, and we said the type of forces that are involved between ethanol molecules. Weak intermolecular bonds or forces. Yep, okay. And we said that to overcome this, that the transfer of energy has to come from the student's hands into the ethanol in the liquid phase, and then that's able to turn it into a gas because we're breaking these bonds. And now their hands feel cool. Okay, I loved that. That was very exciting. Yeah, that's the end of question 1. So that'll be an excellent answer here. I reckon we got like, let's do a different color. This is looking like you write this, maybe a merit. Maybe you write this, maybe that's a merit on its own. Together, an excellence. Yay. A little smiley face. If you've made it this far, then congratulations. You managed to deal with listening to me for a long time. But we made it through question 1, and now we have an easy excellence. Nice. I told you it was going to be easy. See, it all makes sense, right? Enthalpy, that's what we did, right? Yeah, it was sick. Okay, let me know if you want me to do any more of these videos. I could probably go through and do the rest of this paper. I could do some other things. I've done chemistry before. I did NCEA level 2 and 3, and apparently I've got like an honours degree in chemistry, so I hope I know what I'm talking about. But I had a great time, so I hope you did too, and I hope you learned something. Unrelated to NCEA, I always do a fun little album recommendation at the end of my video, so here we go. We can have the first album from Panic at the Disco, A Fever You Can't Sweat Out. What a banging album, so many good vibes in here. Probably my favourite Panic album. The new stuff is definitely not as good. So if you haven't heard it, give it a listen. There's some bangers on here. So yeah, okay, cool. Hope you enjoyed. Okay, bye.